Thank you for coming. I will start right away by a short introduction to the session, which will be followed by 5 presentations and by about 20 minutes of discussion. Okay, so we know well how scientific results and technological developments have greatly improved the understanding of risk causes and have caused the basis and have provided the basis for the prevention of their effects. So in a number of cases, these advancements, however, are slow to reach the attention of decision makers, political decision makers, practitioners, and governments. And so this is one of the reasons to have champions. Champions. Okay, so these are the classical champions, which are examples of how limits in resources or knowledge or capacities can be overcome with a proper approach. And then, if properly disseminated, these examples will be able to attract attention and inspire new ideas and positive actions in many people. Part of today's topic is the presentation of the international initiative established under the Group on Earth Observation, which is called the Geohazard Supersites Natural Laboratories. This initiative, which I have the honor to chair, is by itself a collection of champions, although local in scale, examples of how open science, international cooperation, coordination, and innovation can improve risk management and eventually risk reduction, both at the local scale, national scale, but also now increasingly at the global scale, because we have been growing and we become a global network. After over 10 years of operations, we can say that the supersite approach has demonstrated to be able to improve risk management in several aspects. Still, the supersites have a limited field of action. They are concerned only with seismic and volcanic hazards. They only deal with supporting emergency during volcanic crisis or prevention in most cases. But they still are not dealing with all the phases of the risk cycle. So what we are asking ourselves is if the concept of supersites as examples and of best practices at the local scale can be extended, and how can be extended, for instance, by addressing other risk components, other hazards, other risk management phases. Today, we hope to discuss with you the role and scale of champions in risk management and risk reduction. And to prepare the discussion, we will have 5 presentations, as I said, 2 from supersite experiences, and other 3 from other examples, so champions in their way, which provide evidence of how risk management can be improved by thinking out of the box and innovating communication or risk financing approaches. Okay, I think we can start. Due to time constraints, we will have no questions after each talk, but only at the end, so send your questions through the chat. And we are recording, be informed that we are recording the session, and then it will be placed on the conference website. So Alberto Michelini is the first speaker, which will deal with ARISTOTLE project. Go on, Alberto.
Thank you very much. Can you see my screen?
Yes, we do.
So I'm entering full screen. Can you still see it?
Yes, yes. Go ahead.
Okay. So first of all, thank you very much for inviting us to give a talk in this session. I'm going to talk about Aristotle, or better, Aristotle Enhanced ENHSP. It's a long acronym that means All Risk Integrated System Towards the Holistic Early Warning, Enhanced European Natural Hazard Scientific Partnership. If you have any question, you can refer to these emails that you see below. So this is a project that's been started by the European Commission, or better, the DG ECO European ERCC, which stands for Emergency Response Coordination Center. And basically, it is the realization at the European level that they need to have expert assessment on whenever there is a hazard that's striking somewhere in the world, not only in Europe. These are an examples of a hurricane, a tsunami, a volcano, an earthquake, a flood, and a forest fires. And the main point here is that whenever there is a major natural event, there is a strong need for authoritative, timely, multi-hazard advice. And this is one of the topics that are covered by the ERCC. Note, there is one little thing that you can see as a note at the bottom of this slide. There is an increased realization by the ERCC and the SADC as a whole that scientific knowledge is a fundamental pillar in order to activate prevention and or emergency response activities in case of a disaster. So this is, say, the idea that started some years ago, and Aristotle was the project that responded to this call by ERCC. And what you can see in this picture, it is basically what happens in the very few first hours after a major disaster. There is a great need for information that you see in the red line. And at the same time, there is really little information available. But there is, nonetheless, there are a number of services, most of them, they are automatic services that are provided by the scientific institutions that need to, they can be interpreted. So scientific expertise is very, very important in these very first hours because they can provide a better idea, a better assessment of what is the impact of the catastrophic event. So what we put here, it is what it means, basically. So this is how it started Aristotle. Aristotle put together a number of institutions that are using different automatic services or services that are available very, very soon after a catastrophic event. Mainly we provide in a technical jargon, we make use of web services. And the idea is to have a comprehensive, operational, 24/7 multi-hazard scientific advice that is provided to the ERCC. So these are the Aristotle ENHSP consortium institutions. So you see they are not all of Europe, but a great part of Europe, European countries do participate to the project, which is now starting basically a fourth year. The whole project started in 2016, and now in 2020 we started the third stage of Aristotle, which will last 4 years. This picture basically shows how we operate. So what we have is basically we have a virtual emergency room where there are, on a rotational basis, there are different institutions that are providing what we call the hazard leader for each one of the hazards. And this is the hazard leader for each hazard is responsible in 24/7 to give an assessment of its own hazard and to merge and communicate with the other hazard leaders in order to have a multi-hazard assessment of what is going on. This is a map, a little bit of the actual activations we had in basically 1 year period last year. you see there are different hazards have been activated throughout the world. And in addition to this, we also provide what we call the routine operational mode service, which is 3 times a week, basically an assessment of what is going on. This is a picture, gives you an idea. It was taken a few weeks ago on the potential hazards that are developing within at the, say, November 5th in this particular case. So what is it? Now I conclude. So Aristotle in pills. It's a multi-hazard scientific expert advice service, which is provided 7/24 to the Emergency Response Coordination Center. It operated, this is important, by nationally mandated members and participating states institutions of the EU. The service, let me say, is managed by the service management team. It has a kind of a quite articulated architecture, internal architecture, in order to respond. There are protocols and so on. And basically, so far, we feel that it's been quite successful, and there is a very good cooperation with ERCC. Thank you for the attention.
Thank you, Roberto. If you can stop sharing, and Roberto Rudari will present his talk about the EDRIFT project. Six minutes, Roberto.
Maybe if I'm unmuting, it's kind of better. Can you still see my screen? Yeah. Okay. So basically, I would like, to actually tell you a story about, a successful story, I think, where, we had like a lot of help, for what we can call champions. Some very, very well informed, end users or middleware that was placed between, us, as scientists and the end users. Basically, what we aim to do, so the context, was to enable an innovative way, to devise a trigger for an insurance, parametric insurance, to be used as a disaster risk financing product in the context of the Southeast Asia Disaster Risk Insurance Facility. So, something that would help, states and the sovereign risk to respond, more actively and more promptly, I would say, in the immediate aftermath of an event, by providing, in fact, means, really economic means, really to respond to the event. In order to do that, there was not just one, I would say, project, but there was a sequence of coordinated projects between ESA and the World Bank. And we had, I would say, several champions, intervening there. Chief and foremost, certainly for the satellite application, the working group that we had at ESA that was pushing us towards really like innovation and really transforming the applications into something that, could become operational. And I would say, our main, contact point for this type of product was the Disaster Risk Financing Insurance Program. I see Kat is in the audience. She was definitely one of the engines, for us, one of that stimulated basically our path, towards producing something that from a research product would become an application. We had, helps, for other partners from CAT modelers like Risk Management Solutions, or industry providers like Swiss Re that provided, complementary information. And nowadays we are also interacting with ADB that, is leading us also, to more moving from DRF, to DRM, if you wish. So, really, this cluster of champions really served us, to really go into the right direction, I hope. The goal, was very simple. Actually simple to tell. A little bit less simple, to achieve. Was to mix, in a seamless way and in an innovative way, classical catastrophe modeling, in situ observation and data, and satellite data, so that we could, combine them to have a real-time trigger in terms of defining what would be, the number of affected people by floods. to release a payout and also, I mean, permit and allow, I mean, the different, let's say, disaster risk management agency to interact actually to go on the field with some additional resources. In order to do that, I mean, I think, I mean, the most innovative part was the satellite one. That's really where we really, I mean, tried, I mean, to exploit, I mean, this unique, I would say, I mean, exploitment environment lately. So, I mean, the possibility of really having, I mean, several, I mean, different access points to data. So this innovative, I mean, concept of accessing data and accessing also cloud computing facilities. And what we devised, I mean, in this EDRIFT project was really like a platform, a virtual platform that enable to access, I mean, data and computing resources in a multi-provider environment. So, I mean, this was really important for us because, I mean, it allowed us, and really, I mean, to exploit that in order to determine a unique Earth observation asset from different aspects. I mean, the first one was that the high degree of automation that we could put, I mean, into place, I mean, enabled us to, for example, define a full archive of flood extent, I mean, from, let's say, 2015, I mean, up to now, in order, for example, to have a new way to validate model. Here you see a cross comparison between an empirical frequency map from satellite and a model hazard map. So that's what was one thing that we could do. We did also, I mean, with this, I mean, we had also the possibility to support, for example, the risk profiling by using the satellite data in order to validate and also have some derive, I mean, I would say, spatial pattern of the different scenarios that are used, I mean, to build up the risk profiling. Similarly, I mean, we were able, I mean, also to produce real-time flood maps, I mean, on a very large, I mean, area of interest, for example, or say, I mean, the full extension of Myanmar or another country, in order to have, I mean, always the best updates, I mean, updated information coming from the satellite one. And this comes, I mean, into, so the way it works, the application works is really like it merges, I mean, in situ data, satellite data, the model data, I mean, in order, I mean, to derive, I mean, from each portion of the territory, each river segment, the most appropriate definition of what would be, you know, the flooded area. And from that, I mean, derive in the end, you know, the affected population that is used as a trigger for the insurance part. This enabled us, I mean, really, I mean, to monitoring like full seasons, like in a seamless way. This is an example of the 2019 monitoring, where we started from, you know, July, August, where we had, you know, this peak of the event, down to, you know, September, where, you know, there was this recession of the flooding till, I mean, in the end, I mean, at the end of the season in October, where basically, I mean, the situation was back to normality. Our champions are not have not only, I mean, driven, I would say, our application in the first place, but they are continuously driven even now, you know, the improvements by suggesting improvements in that direction. One of which is, for example, to augment and expand the number of missions that could be used, I mean, to enhance, you know, the satellite mapping. Here you see, for example, a combination, merged combination from Sentinel-1 and Sentinel-2 that will be possibly operational like in the future. And also, I mean, to improve, for example, the SAR capabilities of flood detection in urban areas. You know, I mean, this is a strong limitation of SAR-based satellites. And here, LIST, that is one of the partners here, the Luxembourg Institute of Science and Technology, has exploited, I mean, not only intensity, but also coherence with different polarization, enhancing the capability of detection, for example, in urban areas. That is really like one of the things indicated by other champions as one of the limitations of our approach. In conclusion, I mean, I would say that, I mean, I presented like a work that really from research application went, I mean, to application. And I hope, I mean, this will become like an operational service, like at the end of the year. This is what we are working in the direction for. So basically, I mean, a big thank, I mean, to our champions, and a big thank, I mean, to the full team of partners that really worked, I mean, to make this possible. Thank you. Over to you.
Thank you, Roberto. Charles, can you share your screen and start your presentation. I will introduce Charles because he's a researcher of the Goma Volcano Observatory in the Democratic Republic of Congo, which is one very rather recent, let's say, supersite, volcano supersite, and he has faced many challenges in establishing the supersite. He will explain exactly how a supersite in a very low-income country can do to improve risk management. Thanks. Go ahead, John.
Thank you, Stefano. Thank you all for being there, and thank you for Understanding Risk Forum for giving me the opportunity to discuss with other and present what we are trying to do to improve disaster risk and management here in Goma. So the Goma Volcano Observatory is an official institution that monitors Nyiragongo and Nyamulagira volcanoes, which are the two Africa's most active volcanoes, located in Central Eastern Africa on the border between the DRC and Rwanda. So these volcanoes are very, very active, and just near there's a city called the Goma City, where live about 1 million people. And the volcanoes of the Virunga is a very highly populated region. We also have some, seismic risk which are related to the rift movement. And here we have the volcanoes which are poorly studied and monitored because of few qualified infrastructures. So here there was a need to support the Goma Volcano Observatory, monitor the volcano in order to be able to predict and to inform the decision makers so that the population could be evacuated to safe places. This is why we decided to bring the Virunga region to the global network of super sited, where we have champions in understanding risk. And the aim of the Virunga super site is to help reduce or support disaster risk reduction in the area of Goma. So as a first result up to now is that with the collaboration between the Virunga super site, institutions which are involved in our super site, and also some companies, we were able, through the Copernicus management surfaces, and there we produced potential eruption of the Nyiragongo volcano around the Goma city. And there we produced a reference map in which we went to the field and found all the data that concern the schools, universities, hospitals, churches, all those places where people could be found and which are useful for disaster risk reduction. Also, we produced a map of land use and land cover. We also produced a lava flow hazards map, which is useful for population evacuation planning. We also
Charles, we're losing you, Charles.
Used a network vulnerability in eruption of Nyiragongo. The the champions could support the Goma Volcano Observatory manage the volcanic crisis. So these maps are very useful for both volcano monitoring and risk management. And these were sent to decision makers. Also, the champions, which are scientists and the agencies, are supporting the Goma Volcano Observatory for volcano monitoring. Here we can see how the Cosmos climate data, which are provided the ASI through the Committee on Earth Observation Satellite, are helping monitoring Nyamulagira and Nyiragongo volcanoes. So the data are provided by these agencies and processes by scientists, like an example from IREA, from INGV in collaboration with scientists from GVO. And also we have here collaboration between Mirova, which is a group of universities which provide thermal activity of volcanoes. Here we have the case for Nyiragongo and Nyamulagira, and the data which are useful for volcano monitoring. Also here we have the Centre National d'Etudes Spéciales from France, and through the CHIR, which provide high resolution images which help to monitor both Nyiragongo and Nyamulagira volcano, and the data which are processed and interpreted by scientist champions to help predict the next coming eruption of Nyiragongo. We also have other partners like INGV, like Volcano Disaster Assistance Program, which is a branch of USGS, which provide the training in US or in Hawaii, and also that provide some equipment for ground data collection, and also support us for interpreting the data. So here I can say that our champions, which are scientists from world leading observatories and also agencies who are providing EO data, are champions who are helping through open science. They are helping us to evaluate hazards and risk in the Virunga region. They are also helping improve our early warning capacity in order to better prepare for the next eruption of Nyiragongo. In conclusion, I can say that our experience where the champions have helping us since 2 years maybe serve as a model to be extended to other low to middle income countries where limited qualified human resources and appropriate infrastructures are limiting understanding risk disaster, and where champions could be invited or could go to support disaster risk reduction there. Thank you, everyone.
Thank you, Charles. Can you release your screen? We will have a discussion on. Sara, it's your turn. Sara Barsotti is also presenting the experience of another super site in a very different country, which is Iceland. Still a volcano super site. Go ahead, Sara. Thanks.
Yes. Hi, everybody. Good morning. Thanks, Stefano, and all the organizers to give us the opportunity to contribute to the discussion today by showing the Icelandic case, as Stefano, you were saying, and introducing you, I guess, an example of how a government can exploit state-of-the-art scientific information in disaster response. This contribution is a collaboration between the Civil Protection of Iceland, the Icelandic Meteorological Office, and the University of Iceland. So when we talk about disasters, and particularly natural disasters in Iceland, then we refer essentially to any natural hazards that you could think of. Iceland is very famous for frequent severe weather, storm surges, and avalanches in the country. They have been representing the worst events in terms of death toll. Floodings, they are very frequent because of very active geothermal activity beneath the glaciers. And eventually, as we all know, Iceland is seismically and volcanically very active. I guess everybody reminds the unpronounceable volcano that erupted in 2010. So in this presentation, I will essentially focus on volcanic hazards in a way. But before moving into more detail on exploitation of data, I think it is important to introduce a little bit how works between the decision makers, so the civil protection in Iceland, and the scientists. So since a few decades, a scientific advisory board has been established. And this board is called by the civil protection regularly during non-eruptive times, just to discuss the status and a general overview. Otherwise, it is called on demand when there are urgent matters and essentially within crisis situations like volcanic unrest and volcanic eruptions. So the scientific advisory board brings together experts in different fields, which shows the most recent observational data. They come with an interpretation of them, and somehow they try to address questions about potential hazards and possible evolution, potential scenarios that could be of interest, again, for those supposed to take decision and finding proper mitigation actions. So as Stefano was mentioning, it is important to remind that Iceland, it has been declared a permanent geohazard supersite since 2013. And this has been guaranteeing access to a variety of satellite data that indeed have been targeting our most active regions, essentially volcanically active regions. The Bardarbunga eruption has, as we will see in a while, demonstrated the usefulness of such a service. And in this specific regards, then I selected the 3 of the most recent volcanic crises that we have been following since 2014 onwards. So actually, we start with as I said, with the Bardarbunga Holurun eruption in 2014-2015. This is where it is located in Iceland. It has been an eruption, a 6 months lasting eruption that has been preceded by a couple of weeks of volcanic seismic unrest with lateral propagation of magma withdrawn by the magmatic chamber beneath the ice here, where the caldera is located. Eventually, again, it culminated into an eruption that has been the largest effusive eruption in Iceland since the Laki event in the 1700s. And again, it lasted 6 months. The second test case I'd like to show you is the case for the Erevaikuti volcano. It is located in the southeast of the country. This is one of the most dangerous volcanoes in Iceland because of the potential of huge eruption. We are talking about a VEI6 eruption that entered in an unrest phase in late 2017, and it has been in unrest for 1 full year. So if you check here the timeline of the seismicity, the monthly rate, over a long time period since 2005 till now, you can clearly identify the period when there was a lot of concern because of the reactivation of the volcano. We had a detection of a cauldron that formed in the middle of the caldera, where there is a thick glacier. So due to the increased geothermal activity, a cauldron formed in the middle of the volcano. The last case is the Reykjanes, the main airport, and Reykjavik, the capital area, is very close to, where an unrest started beginning this year. So this was in January 2000. Affecting more than 22,000 earthquakes, and as we will see, a sequence of intrusions. Entering a little bit more into detail about the exploitation of state-of-the-art data, then the Bardarbunga case, again, it represented the first test case of the usage of a variety of satellite products. So the onset of the unrest and the dike propagation itself were identified using a combination of seismic and geodetic data. And throughout the duration of the eruption, the geodetic data and the modeling, they were used to assess the potential evolution of the event and address and estimate the potential hazards. The temporal evolution of the lava fields, it has been also mapped and tracked and traced by using the amplitude SAR images, and it was even possible to track and plot the temporal evolution of the magma withdrawal from beneath the caldera. The second case, I said, this is the Erevayacut, where the geodetic data were crucial in identifying the onset of the unrest and determining the amount of magma. So somehow come with a first estimate about in case this would have been evolved further, which could have been the sites of an expected eruption there. So again, this fed directly into identifying the potential volcanic hazards, and you can see where the deformation has been indeed peaking in this area or accelerating. Finally, the Reykjanes activity ongoing today. So the Reykjanes is special. There are 3 volcanic systems aligned, one next to the other. So it is somehow complicated to decipher what is happening in this region. So specifically seismic and geodetic data combined with the geodetic models. So most of the time we use the inversion of both combined GPS, continuous GPS and INSAR data to come up with estimates about the sites and the location of the magmatic intrusion. As you can see here, we had a sequence of 3 major intrusions occurred here, just 10 kilometers from a village, Grindavik town. And it was essential to understand which systems they were activated throughout the peninsula, because the unrest started in the Reykjanes Peninsula, in the Reykjanes-Vartsengi system here, and then it keeps propagating to the west, to the east, sorry, and now we have the Krýsuvík system, that is the next one, activated with a current inflation occurring there. So I think we can summarize how it has been possible, and currently it is and it will be, use the state-of-the-art data for emergency response in Iceland. So for the Bardarbunga case, the analysis of the data, it has been really used to support the decision eventually to close the area that at the time was at risk for the public. So it was summertime, people that were still accessing the highlands. So there was the need to understand when and how big this area should have been closed. For the Erevayacut case, the analysis and exploitation of the data has been supporting the preparedness in the event the activity would have been escalating further and possibly culminating into an eruption. So the data have been and are always shared with within meeting with the public. The evacuation has been practiced there, and the civil protection in light of data and the advice from the scientific advisory board has been finalizing the evacuation plan for this volcanic area. And regarding the Reykjanes case then, specifically the usage of the data here has been supporting and helping addressing the scientific question about which is the source, where it is located, and which volcanoes is part of the reactivation, and identifying the possible hazard. For the Reykjanes, it is not only volcanic, but the seismic hazard should be considered as well. Again, in this case, the public has been involved and the data has been disseminated through regular meetings with them, and the civil protection has been finalizing the evacuation plan as well for this specific location. I think, again, this has been an example to show how this becomes in practice the exploitation of high quality, state-of-the-art data for emergency response management. Thank you all.
Thank you, Sarah. Thank you very much. Now let's go to the last presentation by Stefan Schneiderbauer.
Thank you. Yeah, hello everybody. Good morning, good afternoon, good evening, wherever you are. Thank you, Stefano, for inviting us. So I will talk about something very different now. We'll talk about the population that is potentially affected by all the hazards we heard about here. So it's about the dynamic exposure evaluation of populations. It's work that we have done here at Eurac Research as a team of researchers together with colleagues of Eurac Research, Katrin Renner and Christian Kofler in particular. So what did we do is that we improved the information about population distribution at different times during the day and over the year by providing time-specific gridded population data. And this data layer about the population is based on a model that preserves the overall amount of population over a given area and time. And it redistributes this population over space and time according to certain rules and regulations yet you have to specify. And we did that as an input data layer for risk assessment, in particular with the goal to improve risk reduction measures and to improve emergency response. So as we can see here on the two pictures, people are mobile. I mean, maybe to COVID times, people are a bit less mobile, but in general, people are highly mobile. And still, almost all available population distribution data sets, which goes and feed into risk assessments, represent just nighttime populations. So they're very static. However, spatial temporal information about population is crucial for many fields, not only for risk assessment and management, but also for lots of activities that deal more with prevention, like spatial planning, or also for traffic management, for climate change mitigation and adaptation, and of course also for any study dealing with migration and mobility. So actually for a more precise risk assessment, it would be great to have higher temporal resolution. And this means that we as data providers, researchers, data providers, improve the data sets of population, in particular the difference of data and meaning of population numbers between day and night, but also looking at differences when it comes to week and weekend times, or the differences between summer and winter, in particularly in touristic areas. So very quickly to the method that we applied. Actually, it is the basic model has been developed by the University of Southampton in the UK. And we have taken that model and improved and adapted it to our test case area in South Tyrol, in particularly to the city of Bolzano and the touristic area in the mountains. How it works is that the model takes the number of population as origins and then looks at how the people move during certain times of the days or during the week times. And then where do they spend the time, most of the time of the day? So here you have the left-hand side, you have the residential areas where the people mainly sleep, and then you have peak times that you may specify on transportation ways, and then at the end you have people staying in various destinations such as schools, workplaces, hospitals, hotels, and so on. This is a result of what we have done for the city of Bolzano. What you see here is basically already a summary of several data sets. What you see is in a pixel size of 100 by 100 meter, you see amount of population numbers. The yellow pixels are the ones where basically the difference between day and night is not so crucial, as we found it out. But where you see the red pixels, these are residential areas where numbers of people are usually during the day in classical data sets overestimated, because people sleep there, but actually during the day they are not there anymore. Where they are, this is mainly the green dots or green pixels. This is the destinations areas. This is places where people work and stay during the day. So here the number of population potentially at risk during a day is usually underestimated by classical data sets. We zoomed in, as I said before, into one area in the more touristic mountain areas of South Tyrol. Here you have a part of the valley close to Soldo, which is a famous ski resort as well. And you have a combination of our population data together with the hazard risk zone map. And you can see in particular here difference of the left-hand side map with the right-hand side, difference in particular between May and August. So May is kind of low tourist time. August, of course, is a high peak time for tourists. And you see here the numbers of daytime and nighttime population, how this differs according to our model. This is all what I wanted to say about this population modeling approach. You see here the email addresses that you can address to if you have any questions. We have published our approach in this publication here. We are convinced that this dynamic evaluation of population distribution is a crucial input data set for over risk assessments, which could be tremendously improved in future times. Thank you very much.
Thank you, Stefan. So we're finished with the presentations, and I guess we can start our discussion. I don't see any questions in the chat, so please, people, do start asking questions. I can share my screen and give you some initial. Okay, so again, so we said at the beginning that these are examples, and although there are many other examples of good practices and scientific advancements, but how the question I've been hearing in these days also at UR is how to rapidly transform these scientific advancements in actionable information. And then also it depends what you mean by actionable information, but especially for countries where there are some important cultural or financial limitations. So as I said, the approach we have been using with the SuperSite initiative was to focus international cooperation and mostly scientific cooperation and resources by the space agencies which support the initiative and provide lots of satellite data for free. And all these focusing of efforts and resources produced some results, although these results are limited to hazards so far. So there are several other aspects that can be approached, like Stefan was showing in the last presentation. I mean, how to improve the population exposure assessments, how to make it dynamical, and so on. And so the idea is to find a way to, okay, we know that international cooperation, capacity development, and funding are needed, but how to stimulate these actions? How to make this as a sustainable process? If anybody has some ideas. Our idea, of course, is to use, let me see the chat, there is a question, actually. Okay, by Tom Sampson. Let me finish, Tom. Our idea is that if we can increase within the approach of the geohazard supersites the number of aspects and sectors which are involved, this could benefit the local decision makers, at least. Okay, let me read again, everybody. You can talk, Tom, and present yourself and give us your view.
Good morning. Good morning. Tom Sampson here from JDA Consulting. Can you hear me there, Stefano?
Yeah. Oh, go ahead.
Yes. Some excellent talks, very informative and interesting. I'm keen to understand how potentially some of the timeliness or the data lag from some of the hazard data collection from Roberto, Sarah and Charles's talks, what the lag time for producing evidence for decision makers could be. So whether we have a slow responding emergency or a quick flash flood, for example, and then how that could be integrated with the day-night exposure that Stefan presented. So it'd be very interesting to see if there's possibilities to link all this together. Thank you.
Quick replies, Roberto and then Stefan.
Yeah,
then,
thank you for the question, Tom. And actually, JBA is involved also, I mean, in this, let's say, in the operationalization of the service. So, I mean, I think, I mean, you have colleagues also that could respond on that. But I mean, from a certain point of view, so in our case, I mean, we have, I mean, delays that, I mean, is in terms of hours, I mean, for the production of, let's say, the final results so people, in our case, I mean, it's not so crucial because, I mean, I would say the product is based on, let's say, on a near real time aspect, I would say. I mean, so there are days, I mean, a few days where, I mean, there are quality checks, I mean, going out, I mean, for, let's say, the payout to be effective. So, I mean, it's not just a crucial point, but certainly, I mean, the high level of automation that, I mean, we are exploiting there, I mean, could really, I mean, shorten really a lot, I mean, the availability of, you know, the final input, I mean, to the end users, basically. In respect, I mean, to mixing it up, I mean, for example, with a population layer like the one Stefan was producing, I mean, for us, it would be very easy to plug it in, and it would be very interesting actually to see what the difference, which I suspect, I mean, would be huge. I mean, it's from a certain point of view. In our case, it would be, I mean, a little bit difficult, I mean, to connect this, I mean, to the risk profiling that we have that is used to negotiate basically, you know, the insurance products that, I mean, is based on a certain estimation. And to do that, I mean, with dynamic, I mean, exposure, it could be done, but I mean, there are challenges, I would say, I mean, to do that. It will be interesting, I mean, to see.
Thank you, Roberto. Sorry to shorten it.
Sure. Go on.
Janet, for Charles.
Yes, I have a question for Charles. Hello, my name is Janet Edwards. I'm working for the Swedish Civil Contingencies Agency in Sweden, and I also work for the group on Earth Observation Disaster Risk Reduction Group. My question is, we really demonstrated well how you use Earth observation data to produce maps that are very important for the safety of the individuals living in the cities near volcanoes. My question is, do you have some comments about how you were able to sell the idea of using Earth observation data to the politicians and to the residents that live there? What kind of a journey did you have to take to get this accepted? You could see the vision of how it could be used, but how did you sell it to the politicians and the public?
Thank you, Janet, for your support and for your interest. Here at the observatory, we receive the data from TOS and the partners, and GVO and other scientists belonging to the Virunga supersite are in charge of processing the data, producing the maps, and then the responsible of the observatory take the data we produced. They send it to the civilian protection, which is part of a committee of risk management in the province of North Kivu, and then it's up to them to disseminate these results we had, and they do it very well. They have a team of people who regularly go in the school, give some lessons about the volcano and all the data we produced, and then tell them, for instance, with regards to the maps we produced, tell them there's a potential for lava flow to go in this area and or not go in this area. And if there's a volcanic crisis, if there's an eruption, for instance, what we produced as road the vulnerability of the road network to lava flows. They tell them, for instance, if there's a crisis, this road could be cut off, and then you have to follow, for instance, the radio in real time, and they will tell you which road to take and which one to not take. So it's a network which is about the communication to bring the result to the population.
Thank you, Charles. Very quick question, Roberto, if you have 1 minute.
Yeah, you have one. I mean, so Stefan, thank you for the very interesting thing. I mean, sometimes, I mean, we forget, we concentrate and focus really like on how to, I mean, really determine the hazard part, and then we forget that, I mean, there are so many obvious, I mean, lacks, I mean, and problems, I mean, into other parts of the risk equation. And we've been, I mean, working a bit, I mean, on that matter. And I mean, one of the interesting things that, I mean, we are trying to do is using artificial intelligence that to map, for example, from webcams, you know, the density of the population in certain sites that could basically derive basically, you know, the probabilities that you were showing, I mean, into the model. How do you think, I mean, would it be easy, I mean, if you have like a spatially distributed, I mean, distribution function, PDF basically of population during the different times of the day to insert into your modeling? I mean, would you be able to exploit them in this possibility, for example, I mean, easily, or would you need to change them in basically the framework?
No, definitely that would help. I mean, what we struggled with is the input data sets that were available. And I think that would be also in other cases, or let's say even more in other cases, a problem. And anything that will help you then to populate your model with data, things that's coming from cameras, but also mobile phone data, of course, would be very helpful. Would improve the results tremendously, or at least also you could use it as a validation, because we always have trouble to validate our results. So that could be fantastically be used in order to improve the model results. Absolutely, yeah. And a combination of modeling with the real time and reality data would be great. Yeah.
Thank you, Stefan. Okay, I'm afraid we are at the last minute and we have to close the session. We didn't have much time to discuss the approach, which is not only related to scientific advancement, how to use these scientific advancements. We still believe that coordinated action and focusing resources is the best way to test and spread the value of these advancements. So we will insist on that. And if you are interested, please contact us at SuperSite Initiative, but also the other speakers. Thank you very much for being with us today, and okay, enjoy the rest of the UR conference.